right, we have Chapter 4, Section 2 continued, logarithmic functions. Graphs of logarithmic functions is a reflection of the graph of the exponential function about the line y equals x. So I believe I had modeled this in class for you, those of you who weren't in class. If you look at this dotted line right here, that's the line y equals x. The red graph right here is your basic exponential function passing through the ordered pair 0, 1. And its inverse function, the logarithmic function, passes through the point 1, 0. And as you see, if you would fold the coordinate plane along that line y equals x, this graph would lie on top of that graph, and hence there is a reflection if you graph them in the same rectangular coordinate system. Okay, so the red graph is base 3 to the power of x, and the blue graph is log with the same base 3 of x. The easiest way to graph these logarithmic functions is to choose the y values, because those are the exponents to which you raise the base 3. And so then you use the y to get the x instead. Okay, because they are inverses, they're opposite functions. Inverse of being inside would be to be outside, and so on. So the inverse of -2, 1/9 would be the opposite, 1/9, comma, -2 as an ordered pair. Characteristics of logarithmic functions of the form log base b of x. The x-intercept is 1, and there is no y-intercept. This, of course, is your basic logarithmic function, not any log functions that would possibly cross the y-axis due to the shifting of your vertical asymptote. For your basic log function, the y-axis is the vertical asymptote. It approaches, but will never cross. If the base is bigger than 1, the function is increasing. If the base is a fraction between 0 and 1, the function is decreasing. The graph is smooth and continuous. It has no sharp corners or gaps. Okay, this was a review. I'm pretty sure you're familiar with this already. If it's not grouped in with the x, that is a vertical shifting either up or down. Horizontal shifting is left, right. Of course, remember, it's always in the direction opposite the sign, so not to the right here to the left, and not to the left to the right. Reflecting, again, we're looking for that leading negative to see if this thing is right side up or upside down. And then, of course, our stretching and our shrinking. This here was just an illustration, another illustration that these functions are inverses about the line y equals x, that there is a reflection across that line. Notice the key ordered pairs right here for your log function 0, 1, for your exponential function rather 0, 1, and then for your log function 1, 0. Again, just illustrating with an exponential function and a logarithmic function, which are inverses of one another, they will have tables that switch their x's and their y's. Okay, so if you have questions on that, please let me know. This right here, the domain of a logarithmic function, is the set of all x, all positive real numbers, right? Because your y-axis is the vertical asymptote. However, the domain of a log function of the form log base b of quantity x plus c consists of all x for which x plus c is greater than 0. Right? You're never going to have a negative number here. Okay, logarithms aren't negative. To what number do you raise some base to get a negative number? It's not going to happen. So if we're finding the domain of something like h of x equals log base 4 of x minus 5, you just simply take the x minus 5 out, set it greater than 0, and solve it. So the domain here, because there's a shifting here, there's a shift 5 units to the right. And so it should make sense that the asymptote is going to shift 5 units to the right. So instead of the asymptote being x equals 0, we're seeing that the asymptote is x equals 5. And the domain starts at 5, does not include the 5. Remember, because that's the line it approaches and never actually gets to. So you need a parenthesis here. Common logarithms. Well, when we have a common logarithm, and you may have seen that button on your calculator that says log, that's pre-programmed to be log base 10. And that's called a common logarithmic function. The function f of x equals log base 10 of x is usually expressed as this. We don't write the base because we understand the base to be 10. Hopefully you added, either if you have a scientific calculator or graphing calculator, the keystrokes into your notes so that you know how to type these in. If you copied this into your notes but didn't actually test it, you should go back and test it to make sure you get these values. I'm told by one student that this one right here, log of 5 divided by log of 2, your calculator, if you have the new TI-30, or not TI-30, if you have the new TI-84, the color edition, you do need to close this parenthesis. It'll open up a parenthesis for 5, but you need to close it before you hit divide. So just be cognizant of that. Here's an application problem. The percentage of adult height attained by a boy who is X years old, so now we're identifying that X is how old the boy is, can be modeled by this function right here, where X again represents his age, and f of X, or the Y, represents the percentage of his adult height. Approximately what percent of his adult height is a boy at age 10? Well, here they're giving us the X. You have to find the Y. So substitute the 10 in, because X is 10. And then do your calculator computation. I would type in log, well, you could type in 48.8, and then the log button, and then 11, and then add 29. We're going to round this to the nearest percent. The percent of the boy's adult height at age 10 is 80%. All right, here it says rapid growth, then levels off log function. So remember, this boy isn't going to grow infinitely, right? So at some point it's going to level off, which is the opposite of your exponential function, where it starts out slow and then rapidly increases. That's what your exponential function does. Okay, properties of common log. Remember, the common log is base 10. These apply to any of them, right? Because b to the 0 is 1, b to the 1 is b. These are your inverse functions, right? Log base b of the same base b raised to the x power equals x. B raised to the power log same base b of x equals x. We can transform this or apply these common properties to common logs as well. Okay, you just have to understand that the base here, if it's missing, is 10. 10 to the power 0 is 1. Therefore, log of 1 equals 0. Log of 10 is 1. Why? Because base 10 to the power 1 is 10. This one here is your inverse property. This is log base 10 of base 10 to the x power equals x. And your inverse property, raising an exponential to the log of the same base 10 equals x as well. Richter scale problem. You'll have one of these on your quiz. So we're just going to simply use this little formula and substitute into it. It's telling me that I sub 0 is the intensity of a barely felt zero level earthquake. All right, so it says here, the earthquake that destroyed San Francisco in 1906 was 10 to the 8.3 times as intense as a zero level earthquake. Its magnitude on the Richter scale is registered at 8.3. If an earthquake is 10,000 times as intense as a zero level quake, right here, it's telling me that I equals this expression right here. 10,000 times I sub 0. What is the magnitude on the Richter scale? Again, you're going to take these values and substitute into this formula. I know what I equals. It equals is 10,000 times I sub 0. I sub 0 is in, they didn't identify this for me. Now, notice when I substitute into this formula, the I sub 0s are going to divide out, leaving me with a log of 10,000. And when I evaluate that, 10 to what power is 10,000? Well, 10 to the 4th. So the magnitude on the Richter scale is 4. Okay. Natural logarithms. This is your logarithm with base e. We talked about e in the interest formula. Okay, so e is a number. It's an irrational number. And this is called the natural logarithmic function. Okay, so on your calculator, you should see the button that says ln. It's right near the log button. Sometimes college professors, teachers will refer to the logarithmic function with base e as the natural log function, or sometimes they'll say ln of x, okay? So that's how we write it right here, ln x. This ln is a logarithm with a natural base. So the function f of x equals log base e of x is usually expressed as this, ln of x. Sometimes people look at this and say ln x. Okay, so ln x is the natural log. The domain of the natural log function is the set of all positive real numbers. That's your basic function. Therefore, the domain, when we're having a shifting, right, that left-right horizontal shifting, consists of all x for which x plus c is greater than 0. We saw that before. You take what's inside the parentheses and set it greater than 0, and then you solve it. Now, keep in mind, when you divide by a negative, you have to flip the inequality symbol. Okay, same rules of math apply. This one here, x squared greater than 0, right? So here, when you solve this, you're actually going to set this less than 0 and then greater than 0. If you remember doing the quadratic inequalities, we had to set up 2 cases. Okay, and that's what this is all about. Now your domain here is negative to positive infinity for the natural log of x squared, except for 0. That would be your asymptote. Okay, so if you have questions on that, please let me know. Moving on to basic properties of logarithms. This is just copied again so that it's on this page. Okay, log base b of 1 is 0. Here are your inverses. This is log base e of 1 equals 0. Why? Because e to the power 0 equals 1. This here, natural log of e equals 1. Why? Because this is really log base e. So e to what power equals e? The power of 1. These are your inverses, right? Log base e of the same base e to the x equals x. And e raised to the power log base e of x equals x as well. Okay, so just remember, if there's no little subscript on the logarithm, that's common base 10. And if you see ln, that's your natural log or your log base e. All right, the property natural log of e to the x equals x can be used to evaluate natural logarithms involving powers of e. For example, the natural log of e squared is 2, right? This is log base e of the same base e to the power of 2 equals 2. Okay, so whenever you see these, ln of e to some power, it's always going to equal the power. Okay, this one here, natural log of 1 over e. Well, we don't want to have this as a fraction, so we're going to convert this fraction to natural log of e to the negative 1. So this is log base e. I'll write that one down. This becomes log base e of the same base e to the negative 1 power. These are inverses right here. And so you're left with the exponent, negative 1. Use inverse properties to simplify. Again, this is log base e, which we'd never write it that way. Natural log takes over this, of the same base e to the power of 25x. Okay, so what does that equal? Well, those are inverses. It equals 25x. This one here, e raised to the power log base e. So this is what we got going on here. Of the square root of x. Okay, again, same base, they're inverses. You're left with this. And we saw those properties before. Another application problem, as the population of a city increases, the pace of life also increases. So we have a formula here. I like to either highlight or put a box around the formula so I don't miss any parts. Models average walking speed W in feet per second for a resident of a city whose population is P 1,000. Okay, so it's identifying for you what the variables are. W is the walking speed, and P is population P 1,000. Find the average walking speed for people in Jackson, Mississippi with a population of 197,000. Now, be careful not to put 197,000 in here, right? Because this is already in thousands. So if you do that, you're going to get the wrong answer. Okay, it's P 1,000. So what is P? 197. That's what goes in here. Okay, and then this part here is calculator work. You should be able to put this here into the calculator. And then once you find that, add 2.74. And so we're going to round this and say about 4.6 feet per second. Okay, so again, if you have any questions, please let me know so I can help you. This here is your assignment. And one more thing I want to take a look at is you'll see a question like this on your quiz. It says, determine without using a calculator which number is greater. Log base 3 of 75. Well, 3 squared is 9. 3 cubed is 27, right? 3 times 3 is 9 times 3 is 27. 3 to the power of 4 is 3 times 3 times 3 times 3, or 9 times 9, 81. All right, so 75 is a number between there. So this number actually is approximately 3 point something. Maybe it's 3.4, 3.5, 3.6, something. Okay? We'll do the same thing here. 4 to the power of 2 is 16, too low. We're not getting to 50 yet. 4 cubed, well, that's right. 4 squared is 16. 4 to the power of 3. Well, what's 16 times 4? Right? 4 times 4 is 16 times 4 is 64. So 50 is a number between these. So remember, when we evaluate this, this is a number between 2 and 3. Like this over here was a number between 3 and 4. We're looking at the exponent. So this is a number approximately let's see, 50 is closer to 64. So I don't know, 2.4, 5, 6. We'll just estimate about 2.5. Doesn't really matter because we can clearly see this number, 3.6, is greater. So that means log base 3 of 75 is greater than log base 4 of 50. Right? So you're looking for the exponent to which 3 would be raised to obtain 75.
15, 10
Sorry about
log,
that.
please.
Sorry about that. Wasn't expecting her to come on with an announcement. So my answer here then is this. Okay, you do not have to write it as an inequality. We're just saying determine without using a calculator which number is greater. Well, log base 3 of 75 is greater. So if you have questions on that, please let me know. There's a homework discussion, there's a Google Meet, and there is class time. Have a great day.